Hey everyone. Um, so diffusion models are known for their state-of-the-art image generation, but they come with major drawbacks, high computational costs, and slow sampling speed. Our motivation is to explore ways to make these models more efficient without compromising image quality. And to address this, we focus on moving the diffusion process into a compressed latent space using LDMs, and enhancing the architecture with transformer-based ideas before evaluating our results with FID, IS, and LPIPS. So for our experiments, we use the ImageNet 100 dataset, which is a curated subset of the original ImageNet. And for pre-processing, we applied the following steps. First, a random horizontal flip with a 50% probability to augment the dataset without changing the semantic content. We then normalize the images to range between -1 and 1 using the formula shown here for stable diffusion training because it aligns with the noise process. For LDM specifically, after normalization, we encode the images using a pre-trained VAE. And finally, the latent vectors are scaled to ensure approximately unit variance for stable and consistent noise addition during training.
For our baseline, we implemented a DDPM scheduler that gradually adds noise in the forward process and removes it step by step during denoising. We also tested DDIM, a deterministic version of DDPM. It removes randomness during denoising, enabling faster sampling with fewer steps. We use the UNet to predict the noise added at each time step. The UNet architecture includes an encoder to downsample and extract features, a bottleneck for compressed representations, and a decoder to upsample and reconstruct the images using skip connections. To improve efficiency, we incorporated a variational autoencoder. The VAE compresses images into a latent space, allowing diffusion to run on lower dimensional data. We also applied classifier-free guidance to inject conditional information without needing an extra classifier, improving control over generation. But finally, we replaced the ResNet blocks in the UNet bottleneck with transformer blocks. This allows the model to capture global dependencies across the feature map, improving long-range context understanding for better denoising. The transformer block follows a two-part structure. First, we apply adaptive layer norm, followed by multi-pass self-attention, and then add a residual connection. Second, we again use adaptive layer norm, this time followed by a feed-forward MLP and another residual connection.
To evaluate the quality of our generated images, we use three common metrics: FID, IS, and LPIPS. FID measures how close the feature distribution of generated images is to that of real images. A lower FID score means better realism and diversity. Inception score measures both how confident and how diverse the generated images are. A higher IS means the model produces sharp, distinct images across many classes. Learned perceptual image patch similarity, or LPIPS, could better capture human perception of visual similarity. So in short, while FID measures global distribution alignment and IS measures diversity and confidence, LPIPS focuses directly on perceptual image quality. Now let's look at the results matrix and image comparison. For our baseline, DDPM achieved the best FID of 32.53 and IS of 5.83, but the image quality lags behind that of the transformer model. Then we added VAE. It did not improve the FID and IS, but significantly reduced the training time. Then we added transformer, which improved the FID and IS over VAE. So we could see that VAE and transformer architecture demonstrates its efficiency in balancing computational time and image quality. Later, we will run with full image size and more epochs to improve performance and add LPIPS metric to justify the image quality. Looking ahead, we plan to implement in two main future directions. First, in accelerated sampling, methods like PNDM can significantly reduce sampling steps while maintaining high image quality. Second, considering model architecture innovations, hybrid model combining swing transformer and UNet are becoming popular and could offer better performance than traditional UNet.